Hello, everyone. Today I want to talk to you about time. Time is something we all experience every single day, every single moment. Yet when you really try to understand what it is, it becomes one of the most mysterious and fascinating aspects of our universe. Let me start with something simple. What do we mean when we say time? Well, we might say time is what happens when nothing else happens. But that's circular, isn't it? We're defining time using the word happens, which already assumes we know what time is. So we're stuck right from the beginning with something peculiar. Now, in physics, we don't really define what time is in some deep philosophical sense. Instead, we define how to measure it. And that's actually much more useful. We say that time is what a clock reads. But then you ask, well, what's a clock? A clock is anything that does something regular, something that repeats in a way we can count. Think about it this way. In the old days, people used the sun. The sun comes up, the sun goes down, and we call that a day. The moon goes through its phases, and we call that roughly a month. The earth goes around the sun, and that's a year. These are all clocks. They're natural repeating phenomena that we use to measure time. But here's something interesting. How do we know these clocks are good clocks? How do we know the Earth is really taking the same amount of time to go around the sun each year? Well, we compare it to other clocks. We might use a pendulum, or the vibration of a quartz crystal, or, nowadays, the oscillation of atoms in an atomic clock. And when all these different clocks agree with each other, when they stay synchronized, we say they're measuring time correctly. But there's a deeper question here. Why do these different physical processes stay in sync with each other? Why does the vibration of an atom have any relationship to the swing of a pendulum or the orbit of the Earth? This is actually a remarkable fact about our universe. There seems to be a universal time that all these different phenomena follow. At least, that's what we thought until Einstein came along. But I'll get to that in a moment. Now, let me talk about something that bothered me a lot when I was younger, and it bothers a lot of people. That is the direction of time, what we call the arrow of time. You see, if you look at the fundamental laws of physics, at Newton's laws, or even at the equations of quantum mechanics, they work equally well whether time is going forward or backward. If you took a movie of planets orbiting the sun and you played it backward, it would still obey all the laws of physics. The mathematics doesn't care which direction time is going. But we certainly care. We know that time goes forward. We remember the past, but we don't remember the future. Eggs break, but they don't unbreak. We grow older, never younger. There's a definite direction to time in our experience of the world. So where does this direction come from if it's not in the fundamental laws? The answer has to do with something called entropy and the second law of thermodynamics. Entropy is a measure of disorder, of randomness. And the second law says that in any closed system, entropy tends to increase over time. Things tend to get more disordered, more mixed up, more random as time goes on. Think about a cup of hot coffee sitting on a table. The heat from the coffee spreads out into the room. The coffee cools down, the room warms up slightly, and eventually everything comes to the same temperature. That's an increase in entropy. The energy has spread out, become more disordered, and you never see the opposite happen. You never see heat spontaneously flowing from the cooler room into the coffee to make it hotter. That would decrease entropy. And the second law says that doesn't happen. So the arrow of time, the direction of time, comes from this tendency toward increasing disorder. We remember the past because our brains are physical systems that form memories, and memory formation is an irreversible process that increases entropy. The entire structure of cause and effect of things happening in a sequence is tied to this increase in entropy. But now, here's a puzzle. If the fundamental laws of physics are reversible, if They work the same forward and backward. Where does this irreversibility come from? Where does the second law come from? This troubled physicists for a long time. The answer is that it's statistical. If you have a system with a huge number of particles, like the molecules in a cup of coffee, there are vastly more disordered arrangements than ordered ones. A broken egg has many more possible configurations than an unbroken one. So purely by chance, by random motion, systems tend to evolve from less probable ordered states to more probable disordered states. And here's the key point. We live in a universe that for some reason started in a very ordered state. The early universe, right after the Big Bang, had very low entropy. Everything was smooth and uniform. And ever since then, it's been increasing in entropy, becoming more disordered and complex. That initial low entropy state is why we have an arrow of time at all. If the universe had started in a high entropy state, a completely disordered state, there would be no direction to time. Nothing interesting would happen. Now let me talk about Einstein and relativity, because this changes everything I've said about time being universal. You see, Einstein discovered that time is not absolute. Time is not the same for everyone, everywhere. Instead, time is relative. It depends on how fast you're moving and where you are in a gravitational field. This is very strange, and it goes against all of our intuition, but it's been proven over and over again with experiments. If you put an atomic clock on an airplane and fly it around the world, when it comes back, it will be slightly out of sync with an identical clock that stayed on the ground. The difference is tiny, but it's measurable, and it's exactly what Einstein's theory predicts. What Einstein showed is that space and time are not separate things. They're woven together into what we call spacetime. And the way you move through space affects how you move through time. If you travel very fast, close to the speed of light, time slows down for you compared to someone who's standing still. From your perspective, everything seems normal. But when you come back, you find that more time has passed for the people who stayed behind. You've traveled into their future. This isn't science fiction. This is how the universe actually works. The GPS satellites orbiting the Earth have to account for both special relativity, because they're moving fast, and general relativity, because they're in a weaker gravitational field than we are on the surface. If we didn't correct for these relativistic effects, GPS would give you wrong positions by several kilometers. What general relativity tells us is that gravity isn't really a force in the traditional sense. Instead, mass and energy curve spacetime, and objects follow the straightest possible paths through this curved spacetime. What we experience as the force of gravity is really just the curvature of spacetime caused by the Earth's mass. And this curvature affects time as well as space. Time runs slower closer to a massive object. If you stood at the surface of a very dense star, like a neutron star, time would pass much more slowly for you than for someone far away in empty space. The ultimate example of this is a black hole. At the edge of a black hole, at what we call the event horizon, time essentially stops from the perspective of someone watching from far away. If you watch someone fall into a black hole, you would see them slow down, never quite reaching the horizon, frozen in time. But from their perspective, they would fall right through in a finite amount of time. Different observers experience time differently near a black hole. Now, all of this raises a profound question. If time is relative, if different observers can disagree about how much time has passed, if time can slow down or speed up depending on motion and gravity, then what is time really? Is it even real, or is it just a useful concept we invented? I think time is real, but it's not what we naively think it is. Time is a dimension of the universe, like space, but with special properties. We can move freely through space in any direction, but we can only move forward through time because of the entropy arrow I talked about earlier. The combination of relativity and thermodynamics gives us a picture of time that's far richer and stranger than our everyday experience suggests. There's another aspect of time that comes up in quantum mechanics, and it's equally strange. In quantum mechanics, particles don't have definite positions or velocities until you measure them. They exist in what we call a superposition of many possible states at once. When you make a measurement, the system collapses into one definite state. This process seems to involve time in a fundamental way. The Schrödinger equation, which describes how quantum systems evolve, has time in it, but the collapse of the wave function, the moment of measurement, seems to happen outside of that normal time evolution. Some physicists think this means quantum mechanics is incomplete, that we're missing something about how time works at the quantum level. There are even more speculative ideas about time at the very foundations of physics. Some theories suggest that time itself might be an emergent property, something that arises from more fundamental things that don't involve time at all. Just like temperature emerges from the random motion of atoms, perhaps time emerges from some deeper quantum properties of the universe. We don't know yet. This is at the frontier of current physics research. Let me also mention something about the beginning and end of time. Did time have a beginning? According to the Big Bang Theory, our universe started about 13.8 billion years ago in an incredibly hot, dense state. As far as we can tell, time itself started at the Big Bang. It doesn't make sense to ask what happened before the Big Bang, because there was no before. Time itself came into existence along with space and energy and everything else. But some physicists speculate that perhaps there was something before the Big Bang, perhaps other universes or some kind of quantum foam from which our universe emerged. We don't know. The physics breaks down when we try to describe the very first moments of the Big Bang. Our theories stop working at what we call the Planck time, about 10 to the minus 43 seconds after the beginning. To go further back, we would need a theory of quantum gravity, and we don't have one yet. What about the end of time? Will time go on forever? As far as we can tell from current cosmology, yes. The universe is expanding, and that expansion is actually accelerating. In the far future, trillions of years from now, all the stars will burn out, all the black holes will evaporate through Hawking radiation, and the universe will become cold, dark, and empty. But time will keep going. Entropy will keep increasing until everything reaches maximum disorder, what we call heat death. Time will continue, but nothing interesting will happen anymore. Of course, these are just our current best guesses based on what we know now. The universe has surprised us before, and it will probably surprise us again. Let me come back to something more down to earth. How do we actually experience time? Why does it seem to flow? Why does the present moment feel special, different from the past and future? This is something physics doesn't really explain. The equations of physics treat all moments of time equally. They don't distinguish between past, present, and future, but we certainly do. Right now, this present moment feels real and immediate in a way that yesterday and tomorrow don't. Some physicists and philosophers think this feeling of flow, this sense of now, is an illusion created by our consciousness. Others think it points to something deep about the nature of reality that we don't understand yet. I don't know the answer. What I do know is that the physics of time is far from complete. We have wonderful theories that work incredibly well, but there are still deep mysteries. The relationship between quantum mechanics and general relativity, the arrow of time and entropy, the nature of the present moment, the beginning of the universe, these are questions we're still working on. And that's what makes physics exciting. We've learned so much, but there's so much more to discover. Time is everywhere in physics. It's in every equation, every experiment, every observation we make. Yet in some ways, It remains as mysterious as it was to the ancient philosophers who first wondered about it. We've made progress, enormous progress, but the complete story of time is still being written, and that, I think, is a beautiful thing. We live in a universe rich enough and complex enough that creatures like us can exist, can think, can wonder about the nature of time itself. We're made of atoms forged in stars, governed by the same laws that govern everything else. Yet we can understand those laws. We can figure out how the universe works. That's remarkable. So when you look at your watch or your phone to check the time, remember that you're not just checking an arbitrary human convention. You're measuring something fundamental about the structure of the universe itself. Time is real. It's physical. It's woven into the fabric of space-time. And understanding it better is one of the great adventures of science. Thank you.